This code creates accessible text-to-speech videos by combining three things into one pipeline. It turns input text into spoken audio. It renders readable on-screen text that visually tracks the narration. And it exports the result as an MP4 through a Flask API endpoint. The main route that does the work is "API, generate video", which accepts JSON from the front end, pulls out the text, voice settings, format choices, and optional intro image, then builds the video from those inputs. At a high level, the accessibility idea is strong because the viewer does not have to rely on audio alone or text alone. The app reads the content out loud, keeps the text visible on screen, and highlights the sentence being spoken. That is useful for people who process information better when they can both hear and read at the same time. For viewers with low literacy confidence. For people with some hearing loss who still benefit from text reinforcement. And for viewers with attention issues who need the visual cue to stay anchored on the current sentence. The code is not using formal caption tracks like WebVTT or SRT. But it does create a synchronized, read-along video experience. The file begins by importing the libraries that support each stage of the workflow. Flask provides the web server and API routes. Requests is used for HTTP calls to text-to-speech services. GTTS provides a fallback speech engine. Pillow. Through image image draw image font and image ops is used to draw text and manipulate intro images. NumPy converts images into arrays for MoviePy. MoviePy handles audio loading, frame generation, and MP4 encoding. The .env loader pulls configuration from a .env file so API keys and other settings stay outside the code. The app also reads environment variables for external services. It supports ElevenLabs, OpenAI speech generation, Telegram notifications, YouTube upload, Google Drive upload, and TikTok upload. That means the core video generator is designed not just to render locally, but also to fit into a wider automation workflow where a completed file can be sent somewhere or published. Even though those upload routes are not the actual accessibility layer, they show that the app is meant to be part of a production pipeline, not just a local experiment. The first major accessibility-related piece is the text-to-speech fallback chain. Inside API, generate video the code cleans the input text by replacing line breaks with spaces. Then it tries to synthesize speech in this order. ElevenLabs first, OpenAI second, and GTTS last if ElevenLabs is skipped or fails. The app falls back to OpenAI. If OpenAI also fails, it falls back again to Google Text-to-Speech. This is important because it makes the narration more resilient. A user does not lose the ability to generate an audio-backed accessible video just because one provider is unavailable or misconfigured. The ElevenLabs function, generate _ElevenLabs _audio takes text, an output path, and an optional voice ID. It checks whether an API key exists, builds a post request to the ElevenLabs text-to-speech endpoint, sends the text and voice settings, and if the response succeeds, writes the returned audio bytes to an MP3 file. It also logs the raw API response to a debug log, which is useful when speech generation fails. That debugging is practical because audio generation issues are often the first place these pipelines break. The OpenAI fallback function, generate _OpenAI _audio works similarly. It checks for an API key, posts to the speech endpoint with model TTS1 HD and voice on X then writes the result to a file if successful. If the request fails, it appends details to OpenAI_debug.log. From an engineering standpoint, this keeps the accessible video flow robust by avoiding a single point of failure in speech synthesis. The final fallback is GTTS. This one is simpler because it is library-based rather than handled through a direct manual HTTP request in your code. The code picks an accent by mapping a short key like as UK or O to the appropriate top-level domain for Google TTS. That allows the same English text to be spoken with different regional voices. For accessibility, voice familiarity matters more than many people expect. A listener may find one accent easier to follow than another. So supporting this choice is a meaningful usability improvement. Once the audio file exists, the app loads it with audio file clip and reads its duration . That duration becomes the master timeline for the rest of the rendering process. This is a key design decision. Instead of guessing how long the video should be from the number of words, the code uses the actual runtime of the generated speech. That means the visual presentation is locked to the narration length, which is exactly what you want in an accessible read-along video. Next, the app determines a font size using choose _font _size from _word _count . This function estimates text density and scales the font down as the word count grows. The comments describe a linear model from very large text for very short content down to smaller text for extremely long content, and the returned value is reduced further before use. The intent is straightforward. Fit more content on screen when the text is long without making short clips look sparse or oversized. That matters for readability because too large text would force excessive line wrapping, while too small text would make the video uncomfortable to follow. There is a limitation here, though. The current function optimizes for fitting content, not necessarily for low vision accessibility. For some viewers, the smallest resulting font may still be too small, especially on mobile screens. So the code is accessibility aware, but it is optimizing a trade-off between compactness and legibility rather than always maximizing readability. The heart of the accessible video behavior is build _text _frame _renderer . This function prepares a frame generator that MoviePy can call at any timestamp during the video. It takes the total audio duration, the raw text, the target frame size, and the font, then pre-processes the text once to make rendering faster. It splits the text into sentences using punctuation boundaries, computes a weight for each sentence based on its character length, wraps sentences into lines that fit inside the available width, and records which lines belong to which sentence. That pre-processing is important because redrawing and recalculating line breaks on every frame would be slow. Instead, the function lays out the text once, caches rendered frames by active sentence index, and reuses them. That makes the frame generation practical even when producing a long video. Accessibility features only help if the app is fast enough to use. So this optimization matters. The way the text is displayed is simple but effective. Each frame is a dark background image. The currently active sentence is shown in a brighter color and gets a blue highlight rectangle. Behind it, nearby lines remain visible in a dimmer gray, so the viewer keeps context before and after the current sentence. This is more helpful than flashing only one sentence at a time, because the reader can anticipate what is coming next and still remember what was just read. That contextual window is a strong readability choice. The function also calculates how many lines can fit vertically and scrolls the window through the text indirectly by choosing which subset of lines to display. It does not animate text upward pixel by pixel. Instead, it keeps the active sentence near the upper middle region of the visible block, showing a chunk of surrounding text. That reduces motion and makes tracking easier, which is good for accessibility. Too much animation can make captions harder to follow, especially for users with vestibular sensitivity or attention issues. To decide which sentence should be highlighted at a given moment, !frame _at_time compares the current timestamp to the total duration and maps that progress onto the cumulative weights of the sentences. Because the weights are based on sentence length, longer sentences receive more time and shorter sentences receive less. This is not true word-level forced alignment, but it is a smart approximation. It avoids the worst problem of naive caption sync, where every sentence gets equal time regardless of length. As a result, the highlight tends to feel reasonably aligned with the speech even without phoneme timing data. There is also a small highlight _delay of 0.35 seconds. The code comments explain that this keeps the sentence highlight slightly behind the audio for a more natural reading experience. In practice, that means the user hears the sentence begin just before the visual emphasis fully switches. That can feel more natural than a mechanically instant jump, although this is subjective and could be made configurable. Inside the "API generate video" route, once the renderer has been built, the app creates a video clip from it and attaches the audio with _audio. Audio. This is the core text-based accessible video. If there is no intro image, the final video is simply this synchronized text animation plus narration. That is the purest expression of the app's accessibility purpose. The code also supports an optional intro image, passed in as base 64 data. The helper decode _intro _image decodes that data, writes it to a PNG file, and returns the path. Later, during rendering, if an intro image is present, the app decides whether the image can be fit directly into the target output size or whether it should be vertically scrolled from top to bottom over the duration of the narration. If the image is not taller than the target frame, imageops.fit is used to crop and fit it. If it is taller, the code resizes it to match the target width, then generates video frames by taking a sliding vertical crop as time advances. That means the app can create two different kinds of accessible videos. One version is text-centric, where the entire visual field is dedicated to readable text. The other is image-centric, where narration plays over a static or scrolling image. The image version can still be useful, but strictly speaking it is less accessible than the text-rendered version because the code replaces the text clip with the image clip rather than compositing text on top of the image. In other words, when an intro image is used, the app currently sacrifices on-screen readable text during the main clip. That is the biggest accessibility weakness in this implementation. The rendering loop supports multiple output formats in one request. It chooses from portrait, landscape, and square layouts. If an image is present, it renders at 1080p variants. Otherwise it uses lighter 720p variants. For each selected format, it creates a file name, builds the visual clip, encodes it with H.264 video and AAC audio, and writes the MP4 file. Those codec choices are standard and broadly compatible, which helps accessibility in the practical sense that more devices and platforms can play the result without conversion. The app exposes render tuning controls as request parameters, including render FPs encode preset and encode threads Lower FPS is acceptable here because the visual changes are mostly sentence switches and occasional image scrolls. not high motion footage. That keeps export times and file sizes lower. From the standpoint of accessibility, that is a sensible trade because the content is informational, not cinematic. After each video is rendered, the app can optionally send a Telegram notification using !send _ to _ Telegram !, and the response from !appy generate video returns a JSON object listing the created videos with their URLs, file names, and render times. This makes the generator easy for a front end to consume. A user can submit text and immediately receive playable outputs. There is also a separate !appy upload video route. That route does not generate the video itself. Instead, it takes a finished file name and uploads it to targets such as Google Drive, YouTube, or TikTok depending on the request. It also returns debug information about whether the target services are enabled and whether client secret and token files are present. That route is operationally useful because it closes the loop between content creation and distribution, though it is not directly part of the accessibility rendering logic. One small thing worth noting is that !extract _ text URL exists in the file but is not called from !appy generate video . That helper can fetch a web page, strip scripts and styles, and return visible text, so the app appears prepared for a future mode where the user could provide a URL and have the page content turned into speech and video. Right now, though, the route you showed expects text to already be supplied in the JSON payload. So, in plain language, the code works like this. A user sends text to the Flask API. The app chooses a voice and creates narration, falling back across providers until it gets audio. It measures the audio length. It calculates a font size suitable for the text length. It pre-processes the text into sentences and wrapped lines. It generates video frames that show the text on a dark background and highlight the sentence currently being spoken. Or, if an image is provided, it uses that image as the visual instead, fitting or scrolling it as needed. Then MoviePy combines the frames and the audio into 1 megapixel 4 file and returns the result. As for why this creates accessible videos, the biggest reasons are synchronized narration, persistent on-screen text, current sentence highlighting, readable contrast, and support for different speech engines and accents. The code is especially good for read-along style content, educational explainers, article narration, and simple voiceover social videos where comprehension matters more than visual complexity. The main improvements I would suggest, if your goal is even stronger accessibility, are these in concept. First, keep the text overlay even when an intro image is used instead of replacing the text clip entirely. Second, add true subtitle export such as SRT or VTT so platforms can use native captions. Third, expose minimum font size and contrast settings as user controls. Fourth, consider word level alignment if you want karaoke-style precision rather than sentence-level approximation. Fifth, add line spacing and safe margin controls for mobile screens. Those changes would move it from accessible style video generator to something much closer to a full accessibility-focused publishing tool. Still, even in its current form, the code already does the most important job. It turns plain text into spoken, visually guided video in a way that is much easier to follow than narration alone.